What about molecules? Well, molecules are more complicated. Most of gas in the air is made up of nitrogen molecules, and each nitrogen molecule has 2 atoms. Now you have a molecule, then not only can you excite transitions in each atom of this type, you can also excite transitions for the molecule itself. The distance between 2 atoms can change, and that can be an excited state, because it's like a spring, right? You can put energy into it, and then you can get the energy out of it. And so molecules have some additional oscillational and rotational degrees of freedom, each of which are associated with new types of transitions. And so molecule spectrum is, it's richer. It has all sorts of bands, not just lines. Moreover, different molecules can scatter light differently depending on the light frequency. And that's what explains the color of the sky. So let me draw a little picture here. So suppose, again, we have to use our mental microscope to think about a molecule of nitrogen scattering light in the atmosphere. So this molecule is exposed to different frequencies of light. Yeah, there's a high frequency, which is blue, and there's a lower frequency, which is red. Of course, in this description, I exaggerate them, right? They are not that different. Well, maybe actually they are. I don't know. Factor 2. So. Right, so then this molecule starts oscillating in the electromagnetic wave of this light. And as it oscillates, it kicks the photons of light in certain directions. And so it is able to scatter blue light more efficiently than it scatters red light. So the blue light gets deflected by bigger angle and more often than the red light. Okay? Now what happens in the atmosphere? The observer looks at the sun through a layer of air, the atmosphere. So sunlight is not perfectly white, but it has all sorts of colors. It has red, blue, green colors. All the colors of the rainbow are included. But then it meets with some molecules that scattered it. So let's look at this ray of light. So in this direction, I have blue and red going apparently to miss this observer. But then some molecules of air, molecules of nitrogen, of course, can scatter blue light more efficiently than they scatter red light. And so the blue light can get turned around. I mean, it doesn't happen in just one scattering. It could be twice. But it gets, or just a small fraction of these photons can be deflected. But the blue light is more likely to get deflected and reach this observer. Now, this observer sees this blue light coming from where? From nowhere, right? It doesn't seem to come from the sky. From the sun. This light comes from the sun. But the light that reaches the observer from other angles has to be rescattered light. And that light is more likely to be blue than red. So that's why when you look away from the sun, you see blue color. that's the most likely kind of deflected light in air. Why do you see the color of the sun change at sunset? Well, it's simply because at sunset, the thickness of the air filter between you and the sun is maximal. When the sun is here, it goes through this much of the atmosphere. If you remain here, this is, okay, so this is Earth, this is sun, right? Sun is very far away. And the Earth, of course, this is not drawn to scale. So this is Earth. Okay? Now, when the sun goes around and is about to set, of course, it's the Earth rotates, okay? But if you're standing on the Earth, it seems that the sun is moving. Right? So at sunset, you see the sun just above the horizon. Now, at this point, the thickness of the atmosphere is much greater than it is in this direction. So this is just a pure geometry. And so the light from the sun, which also contains red and blue components and other colors, is now filtered by more air molecules, each of which tries to get rid of blue. It just tries to kick the blue out, right? It tries to kick the blue out more than it does the red color. And so what arrives here is a redder component, because you lost so much blue on this scattering and deflection. Now, of course, some of the blue is lost here as well, but because this distance is smaller than this, the sun is not as red when it is in zenith, and it's quite red near the horizon. Now, what about clouds? Why are clouds white? Well, it's because they're made of droplets of water. And it's not even just molecules. These are real droplets. I mean, they're tiny droplets, but they're droplets of water. And these droplets are so big that, in comparison to the wavelengths of light, that to these droplets, all colors of light seem to be the same. So they scatter them more or less equally. And that's why they scatter white. They just don't care, red or blue. It's just, they're big enough not to make a difference between these wavelengths. Okay, so now there is and it's actually fascinating, right? That every element has its own fingerprint, because I can take a burner, use something like this or a more sophisticated version of this, spectrometer, and analyze the chemical composition of whatever I'm burning here. So this is done. This is commonly done. That's how people find out the compositions of various substances. So what you do is you place a burner with some sample before your prism. You illuminate it with some light, and then you can see the absorption spectrum. Or you just light it up and give it some energy and make it produce certain lights. And then you analyze the lines that it produces. Right? So what you need to do is to give some source of energy to the atoms, make the atoms go up in higher levels of energy and emit light. And then you just read off the fingerprint of this substance and figure out which elements are there. Are there questions? All right, so I'll see you on Friday then.